Thanks everybody for being here. Going to be talking about this idea of crypto as the sort of like picks and shovels for AI, something you probably heard around in the narrative a little bit, and I want to try to flesh it out and poke at it and discuss it a little bit. If you don't know me, I'm Matt Stephenson. I'm the head of research at Pantera. A little bit about my background. I guess I have research partner here. I don't know which is the more prestigious sounding title, so I'm just trying to impress you, give you both shots, just in case. I'm an econ PhD at Columbia, mostly micro, kind of a game theory approach. I've been in crypto since 2011 is like the cool story, but I've actually been in research crypto only since 2017. ETH Research, a company called Block Science, which is at least kind of familiar more generally in the city, and you might know of it. And then I've done some early writings that, I think have been reasonably insightful about the way things would go, right? So I wrote about blockchains as commitment devices back in the day in 2017, DeSci, RPGF. ML for asset abstraction in 2021 with my colleague Zargam. So to brag on myself a little bit, I think I generally will get to things early and say semi-credible things about them. So hopefully we're going to try to do that today. And that's my Twitter because I usually forget to give it. So I'm mainly coming to you today with a sort of extension of this 2023 paper with some colleagues, with Barnaby and Tomas and Shin and Jonathan and Davide. That we got to present at the AI conference, NeurIPS last year, on cooperative AI via decentralized commitment devices. So the essential angle here is that there's a future in which there are autonomous agents and they transact on chain and they utilize commitment to solve coordination problems, right? And I think we give a pretty robust reason why that would be so. The AI folks bought it, at least the ones we talked to or talked to us. In the TLDR, from a kind of game theory way, is basically if you train AIs in this computationally efficient way, which is called external regret minimization, you wind up with an equilibrium that's not quite non-cooperative. It's not robust to strategic deviations is the idea. What does that look like? It looks like MEV. And so that connection is pretty robust. And the idea that the intuition that it goes to MEV is about right, we think. And so that's the TLDR of that paper. What I'd like to do this talk is extend it and generalize it a little bit. So in particular, that one is about a particular type of multi-agent reinforcement learning. We did that as an example case. But I want to talk about it in a more kind of realistic case, right? What we basically have now is we have these two types of models. We'll talk about this in a minute, right? We have transformers and we have diffusion models, which just kind of appeared on the scene. And those are interesting, but they weren't specifically addressed in our paper. And then I'd like to sort of explore the way those markets might develop and how those might map to different possible futures. So we're going to have to do a little tiny bit of something that feels a little like futurism, which I'm pretty uncomfortable with. As an academic, it's the line is it's always hard enough to predict the past or whatever. But I'm going to do my best here, okay? And then lastly, we're going to talk about this MEV concept a little more in detail as well, right? So we're going to talk about this specifically as being demand incompatibility from a multi-agent future. So why I'm uncomfortable with futurism? There is a tradition of VC futurism, right, where you basically take the set of things you invested in recently, and then you try to map them onto the union of the set of the podcasts you heard recently, and then the two big sci-fi novels you read or whatever, right? And so that's usually the way you kind of do futurism here. Gonna not do that here. But I'm mindful of that tradition, so I'm going to try to not stray from it. Instead, let's try to look at what we have and be a little theoretically grounded. So I said, right, we have two models. They just sort of appeared on the scene. We have a transformer model and we have a diffusion model or an architecture, however you want to say it, right? To my eyes, they didn't appear exceptionally different or better than any other architecture that was proposed, except they happened to work. Don't take it from me, the guy who taught me ML a little bit. David Bly, he said the same thing. He's like, if I show you it on a whiteboard, there's nothing about it that's going to be especially interesting to you, right, compared to any other model. It just so happens that these things work in a really interesting way. They show high returns to data, they show high returns to compute, and they seem to do these just useful things. That seems obvious, so that's baseline. But that gives us three sources of uncertainty. And to be good futurists here, let's try to walk through them with a little bit of logic, right? We have uncertainty about I don't know, what if a new architecture drops from the sky? That's one possibility, right? Just happened to us last year, or actually several years ago, right? But we understood it last year. And then there's more compute and more data, right? Which is the sort of you hang around OpenAI or whatever. That's practically the motto, right? More compute, more data, more compute, more data. They show great returns to both compute and data. So we have uncertainties around how those production functions essentially wind up playing out. So when we talk about these futures, I'm gonna give you like two broad bucket cases, right? One is just this kind of like AGI, ASI, like what does money even mean, man, sort of future. And if we go there, I'm not gonna try to talk about it because like I don't think you can predict anything in that future. I'm not gonna try to predict what crypto AI is gonna be, right? So whenever we go there, I don't know. I'll see you guys in the paperclip maximizer or in our great utopia or whatever it is. But then otherwise, I'm just basically going to say probably we wind up with crypto as picks and shovels. Now, I keep promising that. I'm going to try to deliver on it. It just takes some stage setting, right? So the first path is new architectures. I have no idea what that's going to be. That just goes right to AI utopia. What does that money even mean, man? I don't know, right? Can't really predict that. So we're going to kind of skip that one and just say, well, it seems like we probably only got two that kind of do what we think is especially useful. So I don't know what our probability or our expectation is on this, but I'm skipping it. But now let's talk about returns to compute, right? So let's say returns to compute are like stepwise crazy great, and we have some new crazy thing that's in front of us once we have the new NVIDIA chip or whatever. Well, that's probably, again, our Shoggoth utopia, whatever it is. But in the more realistic case, where just the returns maybe, let's say, continue to be high or even diminish, I think you start to get some market segmentation. Basically, you get what we call in the industry here monopolistic competition, right? Where some people are maybe competing over the high end, right? You're constantly buying the new chip. You're trying to compete on the cutting edge of computation. But for the consumers and other cases, they're happy with a little less, right? So the idea is this is called like satisficing. You can think about it like TVs or something, right? Yes, there's always newer and better and more high-res TVs, but the pace at which people consume them, right? They start to get kind of happy with what they have. It's like things can only be so HD, even if you could make fewer and fewer pixels, right? So in that case, I think you get diffusion. And again, I'm sort of like pushing this diffusion to the crypto picks and shovels argument. Second, we have returns to data, right? If it's the case that returns to data are really high, right, then again, we're in AI utopia. But if it follows some reasonable functional form, right, then we probably start to get market segmentation too. Some companies which can capture data and really, really improve their models may win. That becomes maybe a little unique and different because it's kind of oligopolistic. Maybe it turns out that the prompts you input are really important inputs to the next model, which gives you this kind of like positive feedback loop. That probably tends toward monopoly or oligopoly on some level, on the model level. But I think, again, we can probably imagine that there's still this satisficing element where some people are happy with the cheaper or more differentiated or more specialized product, in which case we at least have some kicking over to this consumer diffusion picks and shovels argument. This is the whole map, just, I don't know, proof of work here. And so I said, now I've got to justify why a blockchain. What I really just gave you is why consumer diffusion, right? Why a blockchain? So I think if you hang around crypto Twitter, you'll kind of get some flavor of like, crypto is like 24/7, always on, super battle-tested financial rails. It's programmable money. I'll disagree with that, by the way. I think that's not essentially an incorrect take, right? But it's kind of the 101, and it's a little hand-wavy, we might say, right? I think the programmable money part winds up being the especially interesting part of that, in my view, because it isn't clear to me why you couldn't do banking 24/7, always on, right? Like, it doesn't seem absolutely impossible that you could never outcompete, right, on that front. It just happens to be the way banking is done today, let's say. So the more advanced one from my esteemed co-author, Davide, he gave a talk last month. He did a nice sort of like, here's why blockchains are an ideal substrate. I'd encourage you to watch his talk at Stanford last month at Erica's Open Source AI Summit. But I'm going to do a sort of specialized version here. I'm going to focus on a particular sort of area of commitments and demand, right? And the reason I do it is my kind of motto is, as a researcher in the space, is if you want to solve a problem, you try to identify the small toy game that the problem essentially is, and then you solve it based on that game. So I was trained as a game theorist, so that's essentially what I do. And what is the toy game, or what is the model? I mean, we're basically trying to look at an agent-based future, right? Like, specifically in the paper, we're looking at this particular use case of you have an AI agent that's maybe, let's say, gonna do your bidding. And so what is the game? What is the toy game we're modeling? Well, that's what we're gonna try to do. Like, what does it look like if you and I have two different competing agents, right? And what happens if we have some objective and they compete on that objective? Well, I'm gonna argue that the demand version of it kind of looks like this. It's going to be a coordination game. That's pretty typical, right? So you have a bottle of wine. You have two patrons with with incompatible demands, right? Each one, let's say, wants the whole bottle, right? And then let's say you have 2 agents tasked to, I don't know, go out to the store and get you one, or send a message for it to be delivered, or whatever it is, right? We should talk a little bit about what it means for the demands to be incompatible. You each want the bottle of wine, but let's say you would actually you'd strictly prefer, right, half a bottle to nothing or whatever, right? You'd like some wine at the very least. And so what this is going to do is it's going to create this kind of like continuum of equilibria where what we'd really just like is the bottle of wine. And so the problem, and I'm going to show you the model in a second, is what happens when our demands are incompatible, when we both send the signal that we both want the whole bottle of wine, right? Like, those are just incompatible demands. The world can't meet those. And that's just to cheat and give you give you a little info ahead. That's the kind of MEV-ish side. If that sounds like MEV, no surprise, right? This is the real-world MEV piece. So what does the game theory sort of toy model version of this look like? This is a really discrete, simplified version of the coordination game. You could actually just sort of draw it as a line, right, with multiple equilibria. But it looks like this. We're just going to say you have 3 things you'd like to get out of the wine, right? Like you could do a low demand, a medium demand, and a high demand. You could say high is like, I want most of the bottle. Mediums, I want half. Lows, I want 1/3, right? And then it just so happens when we both send that signal, if they're compatible, we each get our demand. And if they're incompatible, we're going to say we both get 0. You can say whatever that is, right? Like maybe we pay a penalty. Maybe we just we're frustrated by no wine because our interest couldn't be served. Maybe we just have to send something again, right? Depends on how we want to think about the sort of failure mode of this, but we're just going to call that 0 and the worst outcome. And so if you just follow the logic, right, it's obvious. If we both request half a bottle of wine, we can do that, right? If I request high and you request low, we can do that, and so on, right? But you can also see that if we both request low, we can do that too. We just leave a little bit on the table. And so what I bolded here is like the Pareto frontier, right? The idea that we're each doing as well as we possibly could and getting as much wine as we possibly could. And that's where we'd like to live. So this part is almost silly because it's so straightforward, but I think this is essentially the right way to talk about it, which is if you allow one of these 2 parties in the wine to have a commitment device, right? Which is basically to commit upfront to their demand, then you wind up with the equilibrium that they can sort of enforce, right? So they get to enforce the equilibrium they like, right? If I don't get this, then I penalize myself in some way, thus I'm really going to try to do it. Or if I don't get this, then I'm going to penalize you in some way, right? Like anything that looks like a commitment, a conditional commitment, right? Such that if this doesn't go through, then X bad thing will happen that changes these particular payoffs, means that I get to enforce the equilibrium of my choosing, right? I always get high. Probably shouldn't say it that way. I always get the high payoff. So, right, and of course this is crude and discrete, right? In actuality, you'd get everything but epsilon, right? Because you just have to offer somebody else the minimum so that they agree. So if this is the case, then you just want to deviate to commitment, right? Of course, I'd love to have a commitment device. And sometimes you'll read this as like commitment races or something like that, right? Well, if that's the case, if somebody's going to be better off if they go for a commitment and they're going to get everything but epsilon, I might like to have a commitment structure too. So the idea is just, I would like to go to a decentralized commitment device, which is essentially a blockchain, right? You get to program these commitments. You get to program however you want to model the commitment game theoretically, right? Whether it's self-slashing, whether it's other slashing, whether it's something like that, right? You can credibly commit and you can send the message to somebody else and you could enforce this equilibrium, which means somebody else wants to do it too. And when you I skipped the slide, or I have the slide hidden here. But it turns out, you can trust me on this, that if you smooth the function slightly and you give both people access to commitment, they wind up pretty close to the 50-50. That's where it usually winds up going. Basically has to do with how bad it is when you get really, really far away, right? When you really, when you're a special sort of uncertainty that happens when you're close to demanding it all, right? So here's what we've sort of covered as the futurism part, right? We have this idea that AI tech is going to inevitably diffuse, decentralize, and so on, right? We've decided, or I've contended, that decentralized AI agents are useful. I didn't spend a lot of time defending that one. Hopefully it's in the air enough that seems to be true. OpenAI is doing a lot in this. I can sort of feel to me that it would be very useful. So I sort of took that as given. And then we have this game theory part, which basically says if there's some competing resource that you're both after, then you're better off deviating to commitment, right? And then whatever it becomes, whether it becomes like a Stackelberg game or whether you want to think of it as like a bargaining game or whatever, you can wind up with different outcomes, but essentially the model is going to be around the same, right? And so that would have agents transacting on decentralized commitment devices because that's just incentive compatible if they both want to do it. I don't think I've proven that. I've just sort of like gestured toward it in what I think is a pretty plausible way. And then again, the specific outcome of how these things work out depends on your model, and I honestly don't think there's an answer, is my genuine opinion. But I think the answer would live on a blockchain. At any rate, that is going to be my talk. I'm going to finish a little bit early just so I can save room for questions if there are any. If anybody wants to just bail and go to the party, I understand that too. I'm happy to talk outside. So thank you very much.